Welcome back to this video tutorial. In this video we will discuss about the organization of microprogram sequencer. A microprogram control unit consisting of two parts like the control memory, which contains different set of micro instructions, and a separate circuitry for generating the next address of the micro instruction to be executed. Okay, so the next address generated part of this microcontrol logic organization, which is also known as the microprogram sequencer. The next address generated part of this microprogram control logic, which is also known as the microprogram sequencer. And what is the functionality of this microprogram sequencer? The microprogram sequencer attached to the control memory inspects certain bits of the micro instruction from which it determines the next address for control memory. So this next address generated part of the circuitry is known as the microprogram sequencer. How it performs the sequencing? It performs sequencing by considering certain bits of information from each of the micro instruction which are present in the control memory. There are certain bits of instruction, certain bits of information inside each of the micro instruction indicate the address part. Right? Certain set of bits from each of the micro instruction indicate the address part associated with that micro instruction. That address part indicate what is the next instruction to be executed. So next address generated of our microprogram control logic check the address bits of each of the micro instruction and decide what is the next micro instruction to be executed. Okay, so a typical sequencer provides the following address sequencing capability. A sequencer can perform address sequencing in 5 different ways. What are the facilities for sequencing this address? First one, increment the present address for control memory. This is a sequential micro instruction access technique, that is the increment the present address for the control memory. The content of address register of the control memory, that is the CAR, is incremented after execution of each micro instruction. This is the first capability or the first method of sequencing, that is increment the present address for control memory. That means this control address register associated with this control memory currently holding the address of a particular micro instruction which is currently executing. So in increment method, in order to get the address of next micro instruction to be executed, what we want to perform, just increment the current value of control address register content by 1. So this is the first method of sequencing. Just increment the current content of control address register by 1 in order to get the address of next micro instruction to be executed. This is the first and the basic method of sequencing. And the second method, branches to an address as specified by the address field of the micro instruction. Branches to an address as specified by the address field of the micro instruction. So the control address register now holds the address of a particular micro instruction in which it holds certain micro operation which is currently executing. Instead of the micro operation part, the micro instruction contains an address field which contains the address of certain other micro instruction. So the second method indicate branches to an address specified by the address field of currently executing micro instruction. The currently executing micro instruction consisting of some 16 or 26 bits of information. Among certain bits indicate the micro operation part and the remaining bits indicate address field. Okay, so in order to perform a branching, after completing the execution of the current micro operation, what we want to perform, just check the address field of the current micro instruction and identify what is the address information which is specified in the address part of the current micro instruction. Okay, so after identifying the address location, branches to that location in order to get the next micro instruction to be executed. So this is the second method of sequencing, that is branches to an address location which is directly specified inside the micro instruction which is currently executing. Okay, and the third method is branches to a given address if a specified status bit is equal to 1. So the third bit indicate the significance of status bit. Okay, the third method of sequencing means branching to a specified address location based on the value of status bit. So here we want to consider a special bit, that is the status bit, and we want to consider the current value of the status bit. If the current value of the status bit is equal to 1, then we want to consider the address field of current micro instruction and branches to that location in order to get the micro instruction to be executed next. If the status bit value equal to 0 now, what we want to perform, just increment the current value of our control address register in order to get the micro instruction to be executed next. So the third method is, here we want to consider a special bit of information, that is the status bit. So in order to consider the current value of status bit, if the status bit hold a value 0 or 1, if it hold a value 0, then just perform an increment operation of current value of our control address register in order to get the next micro instruction to be executed, that is incremented by 1 and fetch the next instruction which is present sequentially after next to the currently executing micro instruction. Otherwise, that means if the status bit equal to 1, if status bit equal to 0, just increment the current value of control address register by 1 and move to the next micro instruction. If status bit equal to 1, what we want to perform, we want to branches to an address location which is specified inside the address field of currently executing micro instruction. Okay, so the fourth method is transfer control to a new address as specified by an external source. The fourth method indicates that the sequencer transfers a new address for control memory to start the execution of a new micro operation. The external address transfers control to the first micro instruction in a microprogram routine that execute the specified macro operation. That means this fourth method actually indicates a special case or the starting case of microprogram sequencing. That means if we want to start a particular macro operation or a microprogram routine, we want to specify the starting address of that microprogram routine from external. That is, we want to specify the starting address of a microprogram routine from external source. This is mentioned by this fourth method of sequencing. So in order to start a particular microprogram routine execution, in order to start the execution of a microprogram routine, we want to specify the starting address of that particular microprogram routine from external source. This particular case is mentioned by this fourth one. Okay, and the fifth and the last case of sequencing is, it also facilitates the subroutine call and return method. What is this subroutine calls and return? Subroutine means a main program. The currently executing main program can call another subroutine. The subroutine perform a certain particular task. So after completing the execution of the subroutine, it transfers the control back to the called program. Back to the caller program from which it can resume the execution of our caller program. Okay. we have already learned about the subroutine calling in our first module itself. So just revise the topic. So this sequencing also support the subroutine calling and return. Subroutine calling means we have a caller program. Caller program can call some subroutine. The subroutine is for performing certain particular task. So a caller program can call the subroutine so that the control transfer from this caller program to the subroutine starting. So after completing the execution of the subroutine, the control returns back to the caller program so that it can resume its execution and finally complete its execution. So the sequencing facility capability also support the subroutine calling and returning facility. Okay, so these are the 5 different facilities for sequencing, or the different functionalities of our sequencer. Okay, so this is about the sequencing of our organization of our microprogram sequencer. A microprogram sequencer consisting of multiplexer that selects an address from 4 sources and route it into a control address register. So in order to organize a microprogram sequencer, here we have a multiplexer with 4 different sources or input sources. And here we have 2 selection pins. According to the values of these selection pins, we can select one among these 4 sources as the next micro instructions address and is loaded into the control address register. The value of this control address register indicate the address for the our control memory in order to fetch the next micro instruction. Okay. So what are the other things, or what are the components needed for this organization? The output from control address register provide the address for the control memory. So this multiplexer load from these 4, one among these 4 is selected by this multiplexer and is loaded into the control address register. Okay, this control address register form and address information to our control memory in order to fetch a new micro instruction. The content of the car are incremented and applied to the multiplexer and to the stack register file also. So here we have a stack register. This stack register is kept here in order to support the subroutine call and return. How to perform subroutine call and return? Whenever I'm calling or a main program want to switch into the subroutine call, before moving to that subroutine, we want to store the current main program's return address into the stack register file first. So the caller program, the return address of the caller program want to store inside the register stack register file first, then switch the control to the subroutine. After completing the subroutine execution, pop the return address from the stack register file. That means the return address is now available in the top of the stack, so that we want to pop back the return address with the help of a special stack pointer register. This stack pointer register support for pushing the return address into the stack register, as well as support for popping. After completing the subroutine execution, the stack pointer register support for popping the current return address value which is available in the stack top from the stack register, so that after completing the subroutine execution, it can easily come back to the caller program back and resume its execution. Okay, so here we have the stack register file which will support the subroutine call and return facility. And the register selected in the stack is determined by the stack pointer. That means here we have a special stack pointer register which facilitate the pushing and popping operation on this stack register. Input I0, I1, I2 specify the operation for the sequencer, and input T is a test point for the status bit. Here we have input I1, I0, I2 as well as test input. Okay, this input specify the operation of the sequencer. So based on the value of this input, we can specify what operation want to, or what input among these four, what input want to choose next, which is specified by the value of this input information I1, I0 and I2. And this test input is actually used for testing the value of our status bit. If the value of our status bit equal to 0, we want to perform just an increment operation. If status value equal to 1, we want to branch or jump into a location which is specified in the micro instruction itself. So these are the input needed for our microprogram sequencer. Okay. So for starting the sequencing, or just start for if we want to start the microprogram routine execution, but we want to just initialize the system. How to perform this initialization? The address register can be cleared to 0 to initialize the system, and the clock pulses synchronize the loading into the registers. Okay, so in order to start or activate our system in a proper way, what we want to perform in an initial case, we want to clear this control register. Okay, so in order to start the microprogram routine execution, at the initial stage we want to clear this control register first. And also here we have a clock pulse which is connected with this stack as well as with this control address register. This means this clock pulse is synchronized with all the stack activities as well as the control address register or the next address register unit. So this clock pulse is connected with the stack unit as well as the next address register unit also, so that it synchronize the entire activities of the system. Okay. So here we have this operation. So before moving to this operation function table explanation, just consider this one also. What is the meaning of this first input of this multiplexer? The 0th input indicate that if the multiplexer select the 0th input, or if the selection pin value is now like 0 0, S1 equal to 0 and S0 equal to 0, multiplexer going to choose the 0th input. And this what's the meaning of 0th input? Choose an external address. That means just start a new subroutine or microprogram subroutine execution. Just going to start the execution of a microprogram subroutine execution, so that it want to load the control address register from a new address which is provided by an external source. Okay, if the selection pin hold a value like 0 1, that means this multiplexer going to choose the second or the 1 input as the input to control address register. What's the meaning of this one? This means we want to load an address from our stack register file with the help of our stack pointer register. This situation actually indicate a subroutine is currently executing and it completed its execution, so that it want to return back to the caller program. So in order to return back to the caller program, what we want to do? We want to choose our return address from the stack register first with the help of our stack point register, so that after popping the stack top value, which is the actual return address, so pass that return address to the control address register. Now this is the case of input 1. And what about this input 2? This input 2 means, that means whenever the value of the selection pins become in the form 1 0, S1 equal to 1 and S0 equal to 0, what is the meaning? And this means that here we if it is 2, that means we want to perform just an increment operation, but current value of control address register going to increment by 1 and place the address back into the control address register. That means just a sequential execution of our micro instruction routine. Okay. So just want to increment the current value of our control address register, and which forms the next address of our micro instruction. It is going to be executed next. Okay, suppose our selection pin values like S1 equal to 1 and S0 equal to 1. What's the meaning? The multiplexer is going to choose the third input as the multiplexer output. What is the meaning of these three? That means it perform an branching operation. Branching means in order to branching actually indicate in order to jump into another address location which is not in a sequential order, and usually it takes place in case of what operation? In a non-sequential execution. Okay, that means our micro instruction contains a hold and address information which is not a sequential micro instruction, or we want to jump into a different location from where we get the address of we get the micro instruction to be executed next. That is the meaning of this branch. So whenever this multiplexer chose this third input, it perform a branching operation. So consider this function table with all the input and selection values. What is the meaning? With I2 equal I2, I1, I0, T, S1 and S0. With I2 equal to, here it is represented as a don't care condition. That means whatever value for I2 and T, this is not a case in case of the selection value S1 and S0 equal to 0, 0. So here it is given as S1 equal to 0 and S0 equal to 0 with I1 equal to 0 and I0 equal to 0. What's the meaning of this? With I1 equal to 0 and I0 equal to 0, here it is given as I1 is directly connected with selection pin S1, and how to arrange this S0, how to configure this S0 pin, S0 input of this selection, S0 selection pin of this multiplexer, how to configure this input. Here I1 complemented value is ORed with the test input value which is AND with I0 value. This form the S0 input. Once more, complemented form of I1 is ORed with test input and is AND with I0 input, which form the S0 input here, right? And I2, I1, I0 and test input. Here all the four input values I1, I0, test and I2, all input values are AND together, and the output of this AND operation decide whether to perform this push operation on the stack register. Okay, so this I2 is used only for deciding when to perform our push operation. But I1, I0 and test input, all these are used for setting our selection values S1, S0, and I1 is directly connected with S1, I1 complemented and is ORed with test input, and the resultant values AND with I0 input, which form S0. Okay, so by performing AND operation of I2, I1, I0 and test, the result of this AND operation decide when to perform push operation on stack register. And similarly, the I1 complemented form is AND with I0. I1 complemented form is AND with I2, and the output of this AND operation decide when to perform a pop operation from stack register file. Okay, so this is the configuration of our microprogram sequencer, as well as here we have the separate incrementer unit in order to increment the current content of this car by 1, and similarly have the stack pointer register in order to support for the push and pop operation on the stack register file. So these are the components and the configuration of our microprogram sequencer. So how we configured these components like this. In order to understand the meaning of this configuration, consider this function table. Here the values are input are arranged like this: I2, I1, I0, T, S1 and S0. I2 is don't care here, T is don't care. That means whatever value comes for I2 and T, which is which has no significance in this particular case, if I1 equal to 0 and I0 equal to 0, right? S1 equal to 0 and S0 equal to 0. In order to set this S1 S0 and S0 is 0, we want to put or arrange the input like this: I1 equal to 0 and I0 equal to 0. If I1 equal to 0 and I0 equal to 0, no significance for the input value of I2 and T. What's the meaning? So in order to understand this, consider this diagram with the configuration. I1 is set here 0 and I0 is set here 0. This is the case. We want to set our S1 and S0 as 0, 0. Right? And here given as I1 equal to 0 and I0 equal to 0. Okay. So what is the meaning? If I1 equal to 0 and I0 equal to 0, the I1 is directly connected with S1. So S1 becomes 0 now. Okay. But S0 is an output of this particular combination circuit. So consider this diagram. I0 is 0 here. So this 0 value is AND with the output of this particular sub-circuit. So whatever value is substituted for test, this is not a problem here, or the T value and I2 value has no significance in this case. How it possible? So here I0 is 0. Okay. So for an AND operation, if one among this becomes 0, no need to consider the other value, whether it is 0 or 1. If one among these input of this AND operation becomes 0, then the result is always 0. No need to consider other input is 0 or not. So here I0 equal to 0. So whatever value we applied for T, this has no significance here. Okay. So if I1 equal to 0, I0 equal to 0, both S1 and S0 become 0, because I1 is directly connected with S1. So this 0 value become value for S1 also, and I0 is 0 here. So the one input of this AND gate becomes 0. If one input of this AND gate equal to 0, no need to consider the value of other input. So the other value is based on the test input value. So no need to consider the other value. Whatever value comes for this test value, it has no significance here. Here it is 0. So that output of this AND operation becomes 0 always. So S0 become also 0. So this is the case of 0, 0. If it is 0, 0, this multiplexer select this particular input, 0th input. That means it is going to load an address information for a particular micro instruction from an external source, because here we want to start the execution of a particular micro program routine. Okay. Here we are going to just start the execution of a particular microprogram routine, so that we want to load the starting address of that particular routine from an external source. This will happen when S1 equal to 0 and S0 equal to 0. In order to become S1 equal to 0 and S0 equal to 0, what is the input configuration? We want to set I1 as 0, I0 as 0, and we can assign any value to test input as well as to I2. Here I2 has no significance with this, or it has no role by setting for this for setting the input S1 and S0, because I2 is taken as an input for only this particular AND gate. The output of this AND gate is used for selecting when to perform push operation. So it has no role on setting S1 and S0. Okay, that is why don't care condition for this test input as well as for I2. Whenever this I1 and I0 become 0, 0, the S1 and S0 value become 0, 0, so that the car register is loaded with an external address information. Next is the case I1 equal to 0 and I0 equal to 1. I1 equal to 0 and I0 equal to 1. Consider the case again. I1 equal to 0 and I0 equal to 1. If I1 equal to 0, we can directly connect this I1 with S1. So here S1 becomes 0. And I0 equal to 1. Okay, one input of this AND gate become 1. So now we want to consider the other input also. Here it is, if it is 0 here, no need to consider the other input of this AND gate, but here it is 1. So here we want to consider the other input of this AND gate. Okay, so consider the test input. Here it is 0 or 1. Okay, so this is the case. Here the first input of this OR gate is always 1 here. Why? Because the one input of this OR gate is the complemented form of I1. Here I1 is 0, so its complement is 1 here. If one of the two input of this OR gate is 1, then always its output become 1. Okay, so here I1 equal to 0, its complemented version is taken as the input of this OR gate, one input of this OR gate. So always the output of this OR gate become 1. So no need to consider the value of test input. So whatever value comes for this test input, whether it is 0 or 1, it has no significance here, because I1 has value 0, its complemented form is taken as one input of this OR gate. So the OR gate generate 1 as a result in this particular case. So both the input of this AND gate become 1, so it generate 1 as the output of this AND operation, so that S0 also become 1. So this is the case of setting 0, 1 for S1 and S0. Here S1 equal to 0 and S0 equal to 1, the multiplexer going to choose this particular input. This is the case loading from our stack register. Okay, here we want to load from our stack register. That means we want to pop a particular top stack top value with the help of this stack pointer register. So consider this one. In order to perform this pop operation, which is triggered by the output of this particular AND gate. Okay, so this is triggered by, or it is in this AND gate is inputted by this particular complemented form of I1. Here it is 1 now. Okay, and other input is I0. I0 is already 1. So 1 1 it generate 1. So this AND operation generate 1 as the output. That means it trigger a pop operation from the stack register file with the help of this stack pointer register. So perform a decrement operation, pop the stack top value which is loaded into the control address register. That means this is the case when S1 equal to 0 and S1 equal to 1 and S0 equal to S1 equal to 0 and S0 equal to 1. 0 1 0 1, that is S0 equal to 0 and S1 equal to 0 and S0 equal to 1. 0 1 means decimal 1. So multiplexer is going to choose the first input. The first means the input from the stack top. This is the case of returning from a subroutine execution. After completing the subroutine execution, now the control want to go back to the main program. In order to come back to the main program, we want to fetch or pop the return address from the stack registered file first, then jump to that particular location in order to resume the execution of our caller program. Okay, next, third case. This is the case with I1 equal to 1 and I0 equal to 0. I1 equal to 1, I0 equal to 0. I1 equal to 1, I0 equal to 0. If I1 equal to 1, S1 also 1. I0 equal to 0, the one input of this AND gate becomes 0. Okay, if one input of this AND gate becomes 0, no need to consider about the other input, because 1 is 0, then output must be 0. So this is the case 1 0. 1 0 in decimal means 2. So whenever the value of S1 equal to 1 and S0 equal to 0, the second input of this multiplexer is going to select by this multiplexer. Okay, so this is the case happen when I1 equal to 1 and I0 equal to 0. So no need to consider the value of test input here, because here it has no significance for test input and I2. Okay, what is the case of second? If the multiplexer choose the second as the output, then the current address of control register is going to increment by 1 and is write back into the stack register. Sorry, not in stack register now. The write which is incremented by 1 and is taken by this multiplexer as the input and is going to write back into the control address register. So current value of control address register is going to increment by 1 and write back into the control address register. Okay, whether it perform a write operation into the stack register now, we want to check the case also. After increment, whether it perform a write operation into the stack register now. Consider this. This is the case I1 equal to 1 and I0 equal to 0. Okay, so this particular AND operation here, what are the four input of this AND operation? I2, I1, I0 and test. Here I0 is 0. One among these four input is 0. So always the output of this AND operation is 0. So this particular AND operation does not trigger any push operation. That means after incrementing, it does not push any value onto the stack register. It just increment the value and write the incremented value back into the control register without writing the incremented value back into the stack register file. Why? This is because this AND operation generate a result 0, because here I0 value is 0. One among this four input is 0, so here it generate a value 0, so it does not trigger this push operation. So that after incrementing, it does not write the incremented value into the stack register now. Okay, this is the third case. Now the fourth case, again I1 equal to 1 with I0 equal to 1. Both 1 with I2 equal to 0 and T equal to 0. What is the significance? If both I1 and I0 become 1, we need to consider I2 and T value also. 0 0, 0 1, 1 0 and 1 1. That four possibilities of I2 and T in case of both I1 and I0 equal to 1 1. So consider first case I1 equal to 1, I0 equal to 1 with I2 equal to 0 and T equal to 0. This is the first case, I1 equal to 1, I0 equal to 1 with T equal to 0 and I2 equal to 0. So S1 become 1. So here I0 equal to 1 input of this AND operation is 1. Here we want to consider the other input of AND also. So this for this particular OR gate, one input is 0, because I1 equal to 1, its complemented form is 0 here. So test input is always already set as 0, so its OR operation generates 0. So the other input of this AND operation is 0, so that it generate a value 0 here. So now the case 1 0. If it is 1 0, this means what operation? Thus indicate 1 0. This indicate decimal 2. So it want to perform an increment operation. Okay. So again here I2 equal to 0. So that it does not perform any push operation, because any one of this AND input is 0, it generate a value 0 here, so it does not perform any push operation. So just here it is 10K, so it select 2 input as the multiplexer output, so increment the current content of control address register and write back into the control address register, does not trigger any push operation. Okay, so this is the fourth case, it just perform an increment operation. Next case, I1 equal to 1, I0 equal to 1 with I2 equal to 0 and T equal to 1. 0, 1 with I1 equal to 1 and I0 equal to 1. What is going to happen? This is the case, I1 equal to 1, I0 equal to 1, test input equal to 1 and I2 equal to 0. So S1 is 1 now. Here it is 1. One input of AND operation is 1. This complemented form is 0 because I1 is 1 and test input is 1. So this OR operation generate 1 as the output. So this AND gate has 1 as its input. So the S0 value is also 1. So this is the case 1 1 here. If it is 1 1, what is going to perform? It perform a branch operation. That is going to branch to a different address location which is specified in the current micro instructions address field. Okay, so going to branch to that particular address location. Here the I2 value is 0, so AND gate generate a value 0, so it does not perform any push operation. So here it perform a branch operation only. So consider the case I1 1, I0 1 with I2 0 and T 1. This is the case of branching to a location which is specified in the address field of current micro instruction. Next is the case I1 equal to 1, I0 equal to 1 with I2 equal to 1 and T equal to 0. I2 1, T 0. Okay, this is the case I1 equal to 1, I0 equal to 1, I2 equal to 1 with test equal to 0. If I1 equal to 1, S1 is 1, I0 equal to 1, one input of this AND gate become 1. This is 1, so this complemented form is 0 here. Test is 0, so this OR operation generates 0. One of this two input of this AND operation is 0, so S0 is 0. This is the case 1 0. 1 0 means second input of this 1 0 in decimal is 2. So second input of this multiplexer is going to select as the output of this multiplexer. Okay, and again second input means the incremented form of this control address register. Current value of control address register is going to incremented by 1 and is right back into the control address register in order to indicate the address of the next micro instruction. Okay, so again here I1 equal to 1, I0 equal to 1, test equal to 0 and I2 equal to 1. I2 equal to 1, test equal to 0, I1 equal to 1 and I0 equal to, here again one input, that is the test input is 0 here, so that again this AND operation generate output as 0, so it does not trigger the push operation, just increment and write back. Okay, so this is the case here, just an increment operation when I1 equal to 1, I0 equal to 1 with I2 equal to 1 and T equal to 0. Next, the last case is full of 1. I1 1, I0 1, I2 1 and T 1. What is the case? This is the case. I1 1, I0 1, T 1 and I2 1. If I1 1, S1 directly become 1. If I0 1, one input of this AND become 1. I1 complement is taken here. Test input is 1. One of this two input of this OR operation is 1. So the output of OR is 1. Again two input of this AND become 1. So S0 again become 1. This is the case 1 1. 1 1 means 3 in decimal. Okay. So 3 in decimal means going to branch to a location which is specified in the address field of current micro instruction. Okay. And again here I2 equal to 1, I1 equal to 1, I0 equal to 1, test 1. All the 4 input of this AND gate become 1 now. So the output of this AND also 1. So that it trigger a push operation. That means it want to push the incremented value of this control address register is going to load into the stack register file. Why? Here this AND operation trigger a push now, so that after increment the current value of our control register, the incremented value is right back into the stack register file now. So this is the case of subroutine calling. If all the values are 1, it is going to perform a subroutine calling, so that it branches to a location which is specified in the address field of current micro instruction. So before passing the control to that particular location, it want to store the return address onto the top of the stack register file, so that here it trigger a push operation and the current address of our control register is incremented by 1, which is stored or pushed onto the stack top, which is the actual return address to the caller program. Okay, so this is the case of subroutine calling. Okay, so all these are about the microprogram sequencer. Branching takes place and this is the case of branch to subroutine. These are all about the microprogram sequencer. So understand things properly. Okay, thank you.